Hello again. In this video, or this section, I should say, we're going to introduce limits. And in our modern conception, limits are the foundation of calculus. They didn't used to be. It's actually interesting. Newton and Leibniz, who independently discovered or created calculus, neither of them used limits. Neither of them had formal definitions at all. It's a little shocking from the point of view of a modern mathematician. And eventually it was recognized we really need to be defining stuff. And a mathematician named Weierstrass introduced the limit. And I am going to introduce the idea of the limit with an example. So let's state a problem. An object is dropped from 100-meter height, and we have a height function. Its height in meters after x seconds is h of x equals negative 4.9x squared plus 100. And let's state a goal. And this goal is asking a question not about the height, but about the velocity. It's asking what is the velocity of the falling object after 3 seconds. And we think of it. The function we have, the function we're interested in, these are different functions. But in a previous video, well, I guess I should say we may have seen, since these are optional and supplementary, but we may have seen a relationship between height and velocity in terms of the average rate of change. We did an example of an average rate of change with a height function, and we found that its units were meters per second. We found that the average rate of change of height is the average velocity. The average velocity on an interval from A to B is h of B minus h of A all divided by B minus A. So does this tell us anything useful? I think it does. I mean, we're interested in a specific value of x. We're interested in x equals 3. And we can find, for example, the average velocity on the interval from 3 to 4. H of 3 minus h of 4 over 3 minus 4. And now we have to go to our calculator. I know the quality isn't great. This computer I'm on doesn't have software that I can just share screen with, so sorry about that. But here's, wow, the light is right above us. Here's h of 3, here's h of 4. Does this tell us anything? Negative, by the way, I've mentioned this before, but falling objects have negative velocity. So negative 34.21 meters per second. And this is not the velocity at 3 seconds, but it's the average velocity on this little interval from 3 to 4 seconds. And I suggest that this is telling us something, even though it's not what we're actually looking for. Because suppose I made a claim. Suppose I made the claim that the velocity at 3 seconds is negative 700 meters per second. Is that claim plausible? Does that claim seem likely? Probably most of us would dismiss this. Probably most of us would say, well, if the average velocity on this second is negative 34 or thereabouts, it's extremely unlikely that we were achieving a velocity of negative 700 at the start of this interval. And that gives rise to an idea that the velocity, let me banish that because we don't believe it, the velocity at x equals 3 should be at least sort of close to the average velocity from 3 to 4. And if we're willing to accept this idea, where do we go? I mean, if we're willing to accept this idea, what we've done here is essentially approximate the number we're looking for. This is our goal. The velocity at 3 seconds and what we have here is an approximation of that idea, of that goal. So, question, how can we make this approximation better? Well, let's think this through. Why is this only an approximation? Why isn't this average velocity the exact velocity we're looking for? Well, because velocity changes, because the falling object accelerates, but acceleration takes time. So there was acceleration on this 1 second interval. If acceleration is the problem, how can we have less acceleration? Well, we could look at a smaller interval. So The main idea of this problem is that the average velocity on an interval from 3 to, now let's put a B here, approximates the exact velocity at 3. The reason it's only an approximation is that acceleration occurs on the interval, but acceleration takes time. So the approximation is better when B is close to 3. Let's look at a table of values now. Okay, so my notation in the notes is slightly different than what I'm doing in the video. But if we look at what we have here, we have a table. And these values are the B values. They are the endpoints of the interval. And what we have over here is the average velocities. And we've suggested that as these values get closer and closer to 3, the average velocity gets closer and closer to the exact value at 3. So you see when we have this interval that's just 1/10 of a second, from 3 seconds to 3.1 seconds, the average velocity is negative 29.89. Then we make the interval smaller, 3.01. The average velocity is now 29.449. And the pattern that emerges is that as the number on the left gets closer and closer to 3, the number on the right is getting closer and closer to negative 29.4. So if we buy this idea that x getting closer to 3 means these average velocities are getting closer and closer to the exact velocity, it certainly looks like the exact velocity should be negative 29.4. And that is correct. But what we've introduced here is called a limit. It's what fundamentally makes calculus different from algebra. Because in algebra, we take functions and we plug numbers in. Here, we're not plugging a specific number in. Instead, we're letting these B values get closer and closer to 3, and we're looking at what happens. All right. So why not to let this just be 3? If we want B to be close to 3, well, nothing is closer to 3 than 3 itself. So why don't we just let B equal 3? We can't, because We are looking at this average velocity formula, h of b minus h of a over b minus a. And if we let b equal 3, we would get 0 divided by 0. We would get a division by 0 error. So, limit. The limit of a function as x approaches a number this statement, the limit of f of x as x approaches c equals L, means that as x gets closer and closer to c without equaling c. You saw that up here, right? We're getting closer and closer to 3, but we can't equal 3. So as x gets closer and closer to c without equaling c, f of x gets closer and closer to L. And we can make this very formal, but we're not going to. I mean, even in the regular non-applied calculus sequence, we wouldn't want to get much more formal than this, in my opinion. So if going back to this example, the limit as b approaches 3 of h of 3 minus h of b divided by 3 minus b equals, gonna have to remind myself what it equals. It equals negative 29.4. So this is the idea of a limit. I mean, I guess I could just have given you this, but I think it's important that we have some context so that it's clear we're not just making definitions up to bedevil students. So this is the idea of a limit, and problems like this are why we care about a limit.